The wind screams across the frozen landscape of Yorkshire in February 1315. Inside a stone cottage, a peasant family huddles as temperatures plunge to -20 degrees Fahrenheit outside. The walls are 18 inches thick, yet frost creeps across the interior stones. Outside, livestock freeze solid in their pens. Wells become unusable ice columns. Exposed human skin develops frostbite within 7 minutes. This isn't a brief cold snap. The cold persists for 4 consecutive months, part of the Great Famine period when medieval Europe faced catastrophic climate deterioration. A modern human transported to this cottage would last perhaps 6 hours before succumbing to hypothermia, even indoors. These medieval peasants had no central heating systems, no insulated walls with R30 ratings, no double-pane windows. So how did medieval people survive -20 degree Fahrenheit winters without central heating? The popular image shows medieval people shivering helplessly around inadequate fires, suffering through winters in drafty stone castles. Hollywood depicts the Middle Ages as a time of constant cold and misery, with nobles wearing furs indoors and peasants barely surviving. But archaeological evidence from sites across northern Europe tells a dramatically different story. At the Wharram Percy deserted medieval village in Yorkshire, dating to 1200 to 1500 CE, researchers found sophisticated thermal management systems. At the Hangleton medieval settlement in Sussex, dating to 1250 to 1400 CE, excavations revealed architectural innovations that trapped and circulated heat with remarkable efficiency. Even at the humble cottage remains in West Stow, Suffolk, dating to 1300 CE, archaeologists discovered heating technologies that would impress modern thermal engineers. These medieval people developed survival systems, achieving indoor comfort without burning fossil fuels or consuming electricity. At the Wharram Percy excavation in North Yorkshire, dating to 1200 to 1500 CE, archaeologists from the University of York uncovered something extraordinary beneath collapsed cottage walls. Every peasant dwelling featured a sunken floor design, with living surfaces positioned 40-60 centimetres below exterior ground level. Stone foundations extended 80-100 centimetres deep, far deeper than structural requirements demanded. Chemical analysis of soil layers revealed charcoal concentrations, indicating continuous low-temperature combustion over decades. At the Hangleton medieval village site in Sussex, dating to 1250 to 1400 CE, researchers found wall cavities filled with organic insulating materials. Samples contained compressed straw, animal wool, and clay mixtures achieving thermal resistance values of R8 to R10 per inch, comparable to modern fiberglass insulation at R3.5 per inch. At the West Stow Anglo-Saxon and medieval village reconstruction site in Suffolk, dating to 1300 CE, excavations revealed central hearth systems with sophisticated flue designs. Stone, channels measuring 15-20 centimetres in diameter, ran beneath floor levels, distributing heat throughout structures. At the Cosmeston medieval village site in Wales, dating to 1350 to 1450 CE, archaeologists discovered evidence of communal heating infrastructure serving multiple dwellings. Shared chimney systems connected 4 to 6 cottages, creating thermal networks that maximised fuel efficiency. But here's what made researchers reconsider everything about medieval thermal technology: the fuel consumption rates. Manor records from the Bolton Priory estate in Yorkshire, dated 1298 CE, document firewood allocations of 2.4 cubic metres per household per month during winter. Modern households using wood heat consume 4 to 6 cubic metres monthly for equivalent thermal comfort. Medieval systems achieved superior heating efficiency using half the fuel of contemporary wood stoves. But how did medieval people maintain livable indoor temperatures when outside conditions reached lethal cold? The answer lies in sunken floor architecture that exploited Earth's stable subsurface temperatures. Medieval builders didn't construct cottages at ground level. They excavated living spaces 40-60 centimetres below grade, surrounding living areas with thermal mass that remained at constant temperatures regardless of surface conditions. At depths of 50 centimetres, soil temperature stabilizes at 45-50 degrees Fahrenheit year-round in northern Europe. This geothermal baseline provided passive heating that reduced the temperature differential between interior and exterior by 30-35 degrees before any active heating occurred. The engineering sophistication appears in the construction details documented at Wharram Percy. Stone foundations descended to depths of 80–100 centimetres, creating thermal barriers that prevented ground frost penetration. The sunken floors weren't simply dug pits. They featured rammed earth surfaces, compressed to densities of 1,800 to 2,000 kilograms per cubic metre, matching modern concrete density. This compression eliminated air pockets that could allow cold air infiltration while maximising thermal conductivity with stable subsurface temperatures. Archaeological evidence shows builders incorporated stones beneath floor surfaces at 15 to 20 centimetre depths. These stone layers absorbed geothermal heat during day and released it during night, creating thermal buffering that moderated temperature swings. Modern radiant floor heating systems use similar principles, circulating heated water through floor structures. Medieval sunken floors achieved comparable results using only earth and stone. The unexpected benefit was humidity control. Subsurface positioning naturally regulated moisture levels at 50 or 60% relative humidity, preventing the extreme dryness that makes cold air feel colder and causes respiratory distress. Stone walls alone couldn't prevent heat loss through massive medieval cottage walls measuring 45 to 60 centimetres thick. Medieval builders developed composite wall systems using multiple material layers with different thermal properties. The archaeological evidence from Hangleton reveals sophisticated construction sequences. First, an outer stone layer 20 centimetres thick provided structural support and weather protection. Second, a cavity layer 15 to 20 centimetres wide, filled with compressed organic materials, created the primary thermal barrier. Third, an inner stone or wattle and daub layer 10–15 centimetres thick provided interior finishing and additional thermal mass. This wasn't random construction, it was engineered thermal performance. The insulating cavity fill materials show remarkable sophistication when analysed. Samples from multiple medieval sites contain precisely mixed ratios: 40% compressed straw, 35% sheep wool, 20% clay, and 5% animal hair. This combination wasn't accidental. Straw provides structural rigidity and air pockets for insulation. Wool adds superior thermal resistance at R3.5 to R4.0 per inch. Clay binds materials and provides moisture resistance. Animal hair, particularly horsehair, adds tensile strength, preventing settling and compression over time. Modern testing at the University of York's BioArch laboratory measured thermal conductivity of reconstructed medieval wall fills at 0.0042 watts per metre, Kelvin. Contemporary fiberglass insulation measures 0.040 watts per metre Kelvin. The medieval composite matched modern insulation performance within 5%. The walls also incorporated ventilation channels. Small voids 2 to 3 centimetres in diameter ran vertically through wall cavities at 6 to 80 centimetre intervals. These allowed moisture vapour to escape while preventing bulk air movement, eliminating the condensation problems that plague modern insulated walls. Additionally, the thermal mass of stone layers stored heat during active fire periods and released it gradually overnight, maintaining temperature stability for 8 to 10 hours after fires died down. Even with superior insulation, medieval cottages required active heating systems. The central hearth designs found at West Stowe and Cosmeston represent sophisticated radiant heating engineering. These weren't simple fire pits. They were carefully designed heat distribution systems. The hearths occupied central floor positions, equidistant from all walls, maximizing radiant heat coverage. Stone construction extended 30–40 centimetres below floor level, creating thermal reservoirs that absorbed and stored heat. Archaeological analysis reveals hearthstones selected for specific thermal properties. Sandstone and limestone predominate, materials with heat capacity of 0.9201.0 kilojoules per kilogram Kelvin, meaning they absorb substantial heat energy without extreme temperature increases. But the sophisticated engineering appears in the flue systems. Rather than venting heat directly upward and out of structures, medieval hearths incorporated horizontal flue channels running beneath floors before turning vertical. At the Cosmeston excavations, researchers found flue channels 15 to 20 centimetres in diameter, extending 2 to 3 metres horizontally from central hearths before rising to roof vents. These channels distributed heat throughout floor surfaces, creating medieval radiant floor heating. Stone channel walls absorbed heat from combustion gases, warming surrounding earth and floor surfaces. Modern radiant floor systems maintain surface temperatures of 75–85 degrees Fahrenheit for comfort. Analysis of medieval hearth and flue configurations shows they achieved floor surface temperatures of 65–75 degrees Fahrenheit, slightly lower but sufficient for comfort when combined with superior wall insulation. The horizontal flue design also improved combustion efficiency. The extended path allowed more complete fuel burning and heat extraction before exhaust gases escaped. Modern high-efficiency wood stoves achieve 75–80% thermal efficiency. Medieval hearth and flue systems achieved 65–70% efficiency, remarkable performance for technology developed through empirical observation. The systems also provided cooking surfaces, with multiple temperature zones around the central hearth offering different heat intensities for food preparation. Individual sleeping arrangements would have been thermally catastrophic during -20-degree winters. Medieval households developed collective sleeping systems that maximized human body heat retention and sharing. Archaeological evidence from multiple sites reveals consistent sleeping platform designs, raised wooden platforms measuring 2 to 3 meters wide and 3 to 4 meters long occupied wall sections opposite hearths. These platforms elevated sleeping surfaces 40–50 centimeters above floor level, positioning sleepers in the warmest air layer. Cold air settles at floor level. Air temperature increases 2 to 3 degrees Fahrenheit per vertical foot. The elevated platforms place sleepers in air 3 to 6 degrees warmer than floor temperature without any additional heating. But the crucial innovation was collective sleeping. Manor records and archaeological evidence indicate households of 6–8 people shared single sleeping platforms. This wasn't poverty or lack of space, it was thermal engineering. Human bodies generate 100 watts of heat continuously during sleep. 8 people generate 800 watts, equivalent to a modern space heater. When sleeping in close contact under shared blankets, this heat accumulates rather than dissipating. Modern survival training teaches the same principle for preventing hypothermia. Medieval people implemented it as standard winter practice. The shared sleeping arrangements also reduced the total volume of space requiring heating. Rather than heating individual bedrooms to comfortable temperatures, medieval cottages maintained a single communal sleeping area. This reduced heating requirements by 60–70% compared to modern multi-room. Heating. Estate records from Durham Priory, dated 1340 CE, document textile allocations for peasant households. 4–6 wool blankets per sleeping platform. Layered wool blankets create insulating values of R8 to R12, comparable to modern sleeping bags, rated to 0 degrees Fahrenheit. The social implications extended beyond thermal efficiency. Collective sleeping strengthened family and community bonds, created security during dangerous winter months, and allowed adults to monitor children and elderly members continuously. Passive thermal systems and architectural innovations couldn't alone maintain survival during extreme cold. Medieval people developed systematic caloric loading protocols that maximized internal metabolic heat generation. The human body generates heat through metabolism, with generation rates directly proportional to caloric intake. At rest, in cold conditions, the body requires 2,000–2,500 calories daily just to maintain core temperature at 98.6 degrees Fahrenheit. During winter activity, requirements increase to 3,500–4,500 calories daily. Manor records from the Bolton Priory estate, dated 1298 CE, document winter food allocations providing 4,200–4,800 calories per adult daily, substantially exceeding modern dietary recommendations. The food composition shows sophisticated nutritional understanding. Winter diets emphasized fats and proteins over carbohydrates. Fat provides 9 calories per gram compared to carbohydrates 4 calories per gram, doubling caloric density. Fat metabolism also generates more waste heat than carbohydrate metabolism through the thermal effect of food. Medieval winter diets contained 45–50% fat by caloric content, compared to modern recommendations of 25–30%. Archaeological analysis of food residues from ceramic vessels at Wharram Percy shows winter meals featured salt pork, preserved beef, aged cheese, and fish oil, all extremely high-fat foods. The meal timing also maximized thermal benefit. Estate records indicate winter households consumed their largest meal 2 to 3 hours before sleeping. This timing ensured peak metabolic heat generation occurred during the coldest night hours. Modern nutrition science confirms this strategy. The thermal effect of food peaks 2 to 3 hours after eating, generating 15–20% additional heat above baseline metabolism. Medieval people discovered this empirically. The unexpected benefit was psychological. High-fat, high-calorie winter diets provided satisfaction and reduced hunger stress, improving morale during challenging winter months. Modern Arctic expeditions use identical dietary strategies, loading explorers with 5,000–6,000 calorie high-fat rations. Modern researchers studying medieval thermal systems discovered something humbling. The technologies actually work as well as contemporary heating. The Weald and Downland Living Museum in Sussex conducted comprehensive experimental archaeology from 2012 to 2018, reconstructing medieval cottages using 14th century techniques and materials. Researchers monitored thermal performance during winter months, measuring internal temperatures during ambient conditions of -15 degrees Fahrenheit. The reconstructed cottages maintained interior temperatures of 55 to 62 degrees Fahrenheit using only central hearths, burning 2.5 cubic meters of wood monthly. Modern homes heated to 68 to 70 degrees Fahrenheit consume energy equivalent to 4 to 5 cubic meters of wood monthly, nearly double medieval fuel consumption. The University of York's Centre for Medieval Studies conducted parallel research testing medieval insulation materials against modern equivalents. Wall sections constructed using compressed straw, wool, and clay mixtures achieved R values of 1820 for typical 45 centimetre thick walls. Modern frame walls with fiberglass insulation achieve R values of 1921 for walls 15 centimetres thick. When normalised for wall thickness, medieval construction achieved thermal resistance within 10% of modern technology. Professor James Bond at the University of Oxford studied heating efficiency in reconstructed medieval dwellings. His team found the combination of sunken floors, composite walls, and central hearths maintained comfortable living conditions at ambient temperatures down to -25 degrees Fahrenheit using sustainable wood fuel harvests. Contemporary wood stoves performing no better than medieval hearth systems cost $2,000, $4,000 and require metal fabrication. Medieval systems built from stone, earth, and organic materials achieved comparable performance using only materials available within 5 kilometers of building sites. The validation extended to fuel consumption. Estate records consistently document winter firewood consumption of 2 to 3 cubic meters monthly. Modern experimental archaeology confirmed these rates sufficient for thermal comfort, proving medieval people didn't suffer continuous cold but maintained genuinely comfortable interior environments. The thermal technologies medieval people developed enabled permanent human habitation in northern European climates that challenged survival. Without reliable cold weather protection, the population expansion from Mediterranean regions into Britain, Scandinavia, and northern Germany would have been impossible. The ability to maintain comfortable winter conditions allowed communities to thrive in areas with 5 to 6 month winter seasons, expanding agricultural zones and settlement territories. These innovations enabled the demographic growth that built medieval civilization. The thermal technologies also transferred to other applications. The composite wall systems developed for cottages scaled to castle construction, creating the massive stone fortifications that defined medieval military architecture. The hearth and flue designs evolved into the sophisticated fireplace and chimney systems that appeared in the 13th century, revolutionizing heating efficiency. Knowledge transmission occurred through multiple channels. Master builders trained apprentices in construction techniques, including thermal optimization. Written building accounts from major construction projects documented methods. Guild regulations standardized practices across regions. Yet industrialization nearly destroyed this accumulated knowledge. The introduction of coal heating in the 16th century and later central heating systems made traditional thermal architecture seem obsolete. The abandonment of these techniques represents a catastrophic loss of sustainable heating technology, requiring zero fossil fuel input and minimal environmental impact. However, thermal knowledge survived in specialized contexts. Traditional building methods continued in rural areas into the 20th century. Scandinavian turf houses, Scottish croft cottages, and alpine chalets maintained medieval thermal principles. Contemporary sustainable architecture movements now study medieval construction as viable alternatives to energy-intensive modern heating. Passive house design standards use principles identical to medieval sunken floors and composite walls. The ancient wisdom proves more relevant than ever as societies seek low-energy heating solutions. Medieval people survived -20-degree Fahrenheit winters without central heating through innovations modern thermal engineers recognize as sophisticated and effective. They developed sunken floor architecture that exploited stable geothermal temperatures, providing passive heating that reduced the burden on active systems. They engineered composite wall systems using organic insulating materials, achieving thermal performance comparable to modern fiberglass insulation. They designed central hearth and flue systems that distributed radiant heat throughout floor surfaces with 65–70% efficiency. They organized collective sleeping arrangements that captured and retained human metabolic heat, reducing heating requirements by more than half. They implemented systematic caloric loading protocols that maximized internal heat generation through strategic high-fat nutrition. These weren't primitive people shivering helplessly through brutal winters. They were accomplished thermal engineers who developed empirically tested systems, maintaining genuine comfort without fossil fuels or electricity. The next time you adjust your thermostat on a cold winter evening, remember that medieval Yorkshire peasants maintained comfortable homes at -20 degrees Fahrenheit using only earth, stone, wool, and wood harvested from local forests. Their legacy lives on in every passive house design, every radiant floor heating system, and every sustainable building practice that minimizes energy consumption while maximizing thermal comfort. The cottages lying in ruins across the English countryside represent not humanity's primitive past, but our extraordinary capacity to observe thermal principles, refine construction techniques through centuries, and develop sustainable technologies that worked reliably for over 500 years. These medieval engineers left us more than archaeological sites. They left functional heating systems that modern sustainable architecture movements now study and adapt, proving that sophisticated thermal comfort doesn't require massive energy consumption, just careful observation of natural principles and intelligent design.